Several of you have mentioned within the discussion that you are struggling a little bit with the continuous probability distributions, specifically with the uniform and the exponential. As I have mentioned previously, this is probably your first encounter with both the uniform and the exponential distribution, since we do not discuss those two topics within the prerequisite course Stat 1401. So in a previous video, I created some additional examples for the uniform distribution, and in this video, I want to focus on the exponential distribution. So first of all, you have to be able to recognize that you have an exponential distribution. Well, one of the things that I try to do for this purposes of this course is I try to tell you in the scenario that you're using an exponential distribution. Now, I didn't necessarily write all of the problems, and so that may not be the case. There's a couple of other things that you can do to recognize that it's an exponential. Typically, an exponential distribution has to do with time, time for how long an item may last, like a computer part or a car, a tire, running shoes, or how long it takes for a particular event to be completed. So that can also be a clue that it's an exponential distribution. The other thing that you can look for is when you read the scenario and then you start reading the questions. For the exponential distribution, you have to have a value called the decay parameter. So if you have a question following the scenario that asks you about the decay parameter, then likely you're dealing with an exponential distribution. The other thing that I mentioned previously is that with these problems on your midterm, you will be able to use your notes and the formulas. And so you may want to organize yourself and put all the formulas that you may need together on one page, or it may take several pages. But we previously looked at doing that for a uniform distribution. So if I continue on that page and I label it, put my header in there, exponential distribution, then I can begin to write those formulas. Now, one of the formulas that you might want to write down, but quite honestly, you don't really need, is the function that models the exponential distribution. That function is m, which is your decay parameter, times e, which is the natural number, raised to the negative m x power. Now again, I really don't need that formula for any of my calculations. If I wanted to visually draw and be specific, I could use that to come up with the function to enter into the calculator, but I really don't need that particular function. Things that I do need, I would need the mean, which is represented by mu, and that will be given in the scenario. Okay, typically with an exponential, you have to start out knowing what the mean value is. If you know the mean, then you will also know the standard deviation, because the standard deviation of an exponential is equal to the mean. Okay, which again, I've already told you the mean is given to you. So if you're given the mean, then you automatically know the standard deviation, because for an exponential, they are the same. I mentioned to you one of the important values that you need to know in relationship to an exponential is the decay parameter. The decay parameter is represented by the letter m, and it's equal to 1 divided by the mean. Okay, 1 divided by the mean. And we do use that in the calculations of the probability. So you need to know the value of the decay parameter, which is represented by m. Calculating the probabilities of an exponential function, there are two different ones. It depends upon whether you're doing the area to the left or the area to the right. So there's two formulas that we need to write down. So if we think about first, we want to find the area to the left. Okay, now again, area, remember, corresponds to probability. The fact that it's to the left, you're going to see words like less than. It could be fewer than. We could use the phrase shorter than. And the formula for calculating that particular area, aka the probability, is 1 whole minus e to the negative mx power. Now, if you don't remember, e is called the natural number within the world of mathematics. Okay, so we got a little bit of algebra and statistics colliding here. Okay, it is a value that is pre-programmed into your calculator, and I'll show you where that's located when we get to the calculator here in a minute. The other formula that you need is the area to the right. Okay, area to the right. Again, area is going to correspond to probability. And to the right, you're going to be things like greater than, more than. It could be longer than. And the formula for that one is simply e to the negative mx power. I did miss one because the other formula, and I've run out of space here on my paper. Let me see if it'll let me go to another piece of paper. I don't know if it will or not. Let's see. Nope, not going to let me go. So let me scroll back up just a little bit, see if I can squeeze it in right up here. Okay, this actually goes with exponential, and it's used when you're asked to find a certain percentile. Okay, so when you want to find x or a percentile. You could do the math if you're very familiar with algebra and remember your algebra. You could do the math, but the short formula is your k, they call it k, your cutoff, is the natural log of 1 minus the area divided by negative m, where m is your decay parameter. And again, I would have all those formulas together in one place so that it's easy to refer to them as you're working through the problems. So let's go back over here and begin looking at the problems. So the first problem I have here says the amount of time a bank teller spends with his or her customer can be modeled by an exponential distribution with an average amount of time equal to 4 minutes. Okay, so average is another term or a synonym for mean. And so there's some kind of preliminary questions that I need to answer before I can actually work through some of these problems. And it says, first of all, what is the mean? Well, it tells me in the story that the mean is 4 minutes. And again, that's given to us in the story. It asks me what is the standard deviation. Well, remember, I just told you that the standard deviation is equal to the mean. So because the standard deviation is equal to the mean, The standard deviation for this problem is also 8 minutes. Now, although it's not directly given, that is given in the problem. The third question, which is a very important question, is what is the decay parameter? The decay parameter is m and is 1 divided by the mean. So my mean was given as 4, so my decay parameter is 1/4. Written as a decimal, that would be 0.25. If possible, I would probably use the decimal approximation. So that's what I would use. If you want to look at this visually, and again, I'm not going to draw this to scale, okay, but to give you an idea of what an exponential function could or would look like, again, we would have our vertical scale and our horizontal scale. We would have our time, which is in minutes on the horizontal, and our probability, okay, would be on, not really on the vertical, but we could determine it. So visually, an exponential function in general is going to look something like this. It's kind of an L shape, and it could be going in either direction, okay, whether it's going down, or you could have one that is going up. If you want to be real technical and you like the math and the algebra together, our formula here would be 0.25 e to the negative 0.25x. Okay, but I don't necessarily have to have that in order to work the problem. I don't necessarily have to have the visual of this particular problem to work it. I mainly need to know if it is going to be to the left or to the right. Okay, but if you're interested and you like the visual, there it is. Okay, so we have a scenario. We know that we have an exponential distribution with a mean of 4, and our decay parameter is 0.25. Okay, so the first question says, find the probability that a bank teller spends less than 5 minutes. So it might help you again to rough sketch this, and it doesn't have to be a perfect drawing. If I want to think about it, and I have my drawing of an exponential, okay, and we know that our mean is 4, and we want to say less than 5. The picture's mainly going to help me see, okay, I've got to do less than, okay, or to the left. The fact that this says less than is going to be to the left. And the fact that it is to the left tells me which formula to use. The formula for left is 1 whole minus e to the negative mx. Okay, I have all of the values already. Okay, e is a constant. It's programmed into my calculator. M is my decay parameter, which we know is 0.25. And then x here is given in the problem as 5. So x is 5. So it becomes a kind of substitution problem. We plug and chug. We have 1 minus e to the negative 0.25 times 5. Now, I'm going to go over to the calculator and show you how to enter that directly into the calculator. Okay, so I'm going over to my calculator, and we need to enter 1 whole minus, and then I need to pick up the E. If you look on the left-hand side of your calculator, find the button that says LN. Above it in blue, it says e to the x. So I have second ln, see, and it pops up an e, and then I want negative 0.25 times 5, and then I want to arrow out of the exponent, so I'm going to press arrow, and then I'm going to press enter. Oops, I typed something wrong. See, it told me I did something wrong. Oh, I did. I used the wrong button instead of minus. So let me get back out of this. Okay. And now I'm going to press enter. And I get this value of 0.7134. Okay, so let me write this down. So this is 0.7134 3495 . I believe it will usually ask you to round to 4 places. So the 4th place is a 4. Next door is a 9, which is going to bump it. So it's 0.7135. So the probability that a bank teller spends less than 5 minutes with customer service, with their customer, is about 71%. Okay, about 71%. Okay. Let's look at another one. Same scenario. We've got the bank teller, average of 4 minutes. We want to know the probability that we spend more than 8 minutes. Okay, again, you got to pay attention to the words, guys. This one says more than 8 minutes. So more than implies we're going to be to the right. Again, if it helps you to see it visually, okay, again, you would have your exponential distribution, okay, that looks roughly something like this. We know that our mean is 4, and we want to be greater or more than 8. Okay, and more than is always going to be to the right. Again, you have to recognize that it's to the right because that's going to help you identify the formula. When it's to the right, you're trying to figure the probability that x is greater or more than 8. Okay, so this 8 is your x value, and the formula is e to the negative mx. Remember, m is your decay parameter. So I have e to the negative 0.25 times the value of 8, which was given to me in the problem. Again, at that point, I go out to my calculator. Okay, so let me clear this out. Again, to get the E, it is the blue second button and then LN, and I have negative 0.25 times 8. Get out of the exponent by the arrow and hit enter. And we get 0.135335. Okay, so we get 0.135335. Again, typically you're going to be asked to round to 4 decimal places. The 4th place here is a 3. Next door is a 3. It doesn't round, so we have 0.1353. Guys, please don't overthink it, but you do have to pay very close attention to the words. Now, the next problem, in my opinion, is probably not necessarily the hardest, but it is somewhat of a special case. Okay, because there's not a direct formula. If you'll notice, I gave you a formula for left and I gave you a formula for right, but we didn't have one for the word between. Okay, so the between is a special case. We actually have to do the area to the left of the high value minus the area to the right of the low. And let me see if I can show that to you visually so you can kind of see what we're doing. Okay, so if we have our exponential function, okay, our mean is 4, but we're interested in the value between 4 and 6. So I need this region right here. If I calculate, and I'll color code it here, if I calculate the area to the left of 6, area to the left of 6 would be this region here in the purple. If I then calculate the area to the right of 4, that represents this region. And if you'll notice the overlap, if you subtract the two, where you have the overlap is actually the between. Okay, but you cannot do it directly. You have to do two separate calculations. Okay, so I'm going to first do the probability that x is less than 6. That's left of the high. The formula for left of high for doing left is 1 minus e to the negative mx. Okay, so I still know that my decay parameter is 1/4, so I have 1 minus e to the negative 0.25 times 6. And I'm going to go out and do those calculations. Okay, so I have 1 minus second ln negative 0.25 times 6. Get out of the exponent with the arrow and enter. Okay, so I get that value of 0.7768698399. Now I'm going to actually save that in my calculator's brain. Right above the on button on the left hand side, you see a button that says STO, shorthand for store. So I'm going to store it, and then I'm going to choose one of the green letters, and I'm going to tell it alpha A. So I've stored that in my calculator's brain as letter A. let me write it down for us. Okay, so here we get 0.7768698399. Okay, so we've got that held in the calculator's brain as A. Now I got to start over, okay, and I've got to do the probability that X is greater than 4. This is right of 4, which is my low. Okay. So the formula for right is e to the negative mx. So I would have, let's see, e to the negative 0.25 times 4. And I'm going to do that calculation. Okay, so we have second ln negative 0.25 times 4, okay, gives us 0.3678794412. Okay, now I'm going to leave that in the calculator's brain for a minute. Just leave it sitting there. And I'm going to write it down. So I have 0.3678794412. Now you can retype those numbers in, but eventually what you've got to do is to subtract those two numbers. Okay, so I've got to subtract 0.7768698399 minus 0.3678794412. Now you can retype them, but I can also go back and have my calculator do it for you. So I'm going to recall my A value. So we go second, store, I put it in alpha A, so I'm recalling it, minus the answer that is currently in the calculator's brain, and we get 0.4089903987. Okay, so when you do that subtraction, and if you don't carry all the decimals, and you round early, you're going to get a slightly different answer. So just be careful. 0.4089903987. Again, rounding to 4 decimal places, you have a 9 in the 4th place and a 9 next door. So it's going to bump it, but when that 9 gets bumped, it bumps to 8. So this will become 0.04090 if you round it to 4 places. Again, that was a little bit trickier and it takes longer because you have to do both the left and the right. All right, then the next one, it says 75% of all customers are finished within how long? And that's just another way for them to ask you to find the 75th percentile. Okay, to find the 75th percentile. Again, if you're visual and you want to kind of see what's going on here, again, we have our exponential distribution. And we want to show that 75%, so we're going to have this red shaded region would be 0.75 or 75%, and we want to know what value that would correspond to. How long are they, with the bank teller? Well, again, we can do a lot of math. But again, the easiest way to do it is to use the formula that I gave you just a minute ago. The formula for this problem for figuring k is the natural log of 1 minus the area divided by the negative of the decay parameter. So again, if you'll use the formula, have the formula available when you're taking the midterm, when you're working on your homeworks. Okay, so here I would have k equals the natural log of 1 minus 0.75, because that's what was given, divided by negative 0.25. That was my decay parameter. So I have the natural log of 0.25 divided by negative 0.25. Now those values aren't always the same. It just so happens in this particular problem. So then I'm going out to my calculator. Let me clear all this out. Okay, we're going to use the ln button this time. So we have the natural log of 0.25, close the parentheses, divide that by negative 0.25, the negative of the decay parameter. And we get 5.5451. Okay, so we get 5.5451. So roughly, they're going to spend about 5.5 minutes with a customer, or the customer is going to be there for approximately 5.5 minutes. Again, guys, pay attention to how it asks you to round. All right, let's do another series of questions. On average, a pair of running shoes can last 18 months if used every day. The length of time running shoes last is exponentially distributed. So again, in this problem, it tells us that it's exponentially distributed. I also noticed that later on it asked me for the decay parameter, which is another clue that I'm doing an exponential. It says on average, average is another word for mean. A pair of running shoes that's used every day lasts 18 months. So my mean is 18 months. If I know the mean, I know the standard deviation because it's the same. So my standard deviation is 18 months. My decay parameter is 1 divided by the mean. So in this case, it would be 1/18th. Let's see if that's a nice decimal or not. 1 divided by 18. Okay, that's going to give us 0.05555 repeating. So probably in your calculations, it's better to use it as a fraction, just to be more exact, than to use a rounded decimal. Okay, so the first problem says, what is the probability that a pair of running shoes last more than 15 months? So again, if you have your exponential, okay, and we know that the mean is 18, and we want to know that if they last longer or more than 15. So visually, you're looking for this shaded region. The fact that it is more than is to the right, and the formula for right is e to the negative mx. My point of interest here, my x, is 15. So I would have e to the negative 1/18th times 15. Okay, so I'm going to go ahead and work that out a little bit. E to the negative 15 over 18. I'm going to go ahead and do the multiplication there. Remember, you multiply the tops, you multiply the bottoms. So then I'm going over to my calculator. Okay, so on my calculator, second ln, my e pops up, negative, and I'll put my parentheses, 15 divide 18, close them up, enter, and I get 0.434598 and so forth. Okay, so we get 0.434598 dot 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 dot. Again, typically you're asked to round to 4 places. The 4th place is a 5. Next door is a 9. It'll get bumped. So we have 0.4346. It's not necessarily difficult, guys. You just got to know which formula to use, which means you have to pay attention and read carefully. All right, so the next one, same scenario. It says, what is the probability that a pair of running shoes last less than 12 months? So again, visually, you have your exponential function. The mean is 18. We want to be less than 12. Okay, less than implies we're to the left. If we're to the left, the formula is 1 minus e to the negative mx. My x, which is my point of interest given in the problem, is 12. Okay, so I'm going to plug it in. I have 1 minus e to the negative 1/18 times 12. Okay, so 1 minus e, 1 times 12 is 12. 18 times 1 is 18. And then I'm going over to my calculator. Okay, so to the calculator we go. Let's see, we have 1 whole minus ln second e negative parentheses 12 divide 18 equals 0.486582. Okay, so we get, whoops, wrong one. We get 0.48, and I forgot my numbers, 486582 dot 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 dot. Again, remember we round to typically 4 places, so 5 is in the 4th place, 8 is next door, it's going to get bumped. So we have 0.4866. Then we get back to our special case where it asks us to do between. So visually with the between, we would have our exponential distribution. The mean, which is 18, is in the middle. And we want to know that whether or not our shoes last between 20 to 24 months. So again, special case, we have to do the probability that x is less than 24, that's left, of the high, minus the probability that x is greater than 20, which is right of low. Whoops. So I have to do two calculations. Okay, so if I'm doing left of 24, my formula would be 1 minus e to the negative 1 over 18 times 24. So we have 1 minus e to the negative 24 over 18. Okay, so I'm going out to my calculator and I'm going to do that calculation. We have 1 minus second ln negative parentheses 24 divide 18, close them, enter. 0.7364. Again, I'm going to store it. I'm going to use alpha A again. I don't need the other number. Okay, so I have 0.764. Let me get all the numbers here. 028. 619. Okay. Then we need to do right of 20. So we want to do e to the negative 1/18 times 20, which is e to the negative 20 over 18. So I'm going out to my calculator. Second ln negative parenthesis 20 divided by 18. I get 0.3291. So I get 0.3219. Oh, 91, excuse me. My fault, got an error there, read it wrong. 919 29878. 29878. Then we're going to subtract those two numbers. Okay, we're going to subtract those two numbers to get our final answer. So I'm going to have my calculator recall the one that I stored in its brain, subtract the one that's in its brain now, and we get 0.4072. Ooh, can't remember the numbers. 4072 09 8741. Again, if I round to 4 places, which is typically the request, I would have the 2 in the 4th place, 0 next door. It doesn't get bumped. So I'd have 0.4072. Okay, here's a different question that we didn't see on the previous example, but it's one that I'm fairly certain that you see on some of the questions on your homeworks and on the test. It says, on average, how long would 6 pairs of running shoes last if they are used one after the other? So you go to the store, you find this marvelous pair of running shoes, and you buy 6 pair. So you put on the first pair, and you're going to wear them every day and run in them, and on average, they would last 18 months. That's what it tells us in the problem. As soon as they go bad, you put on the second pair. They're going to last 18 months. And then you put on the third pair. And then you put on the fourth pair. And then you put on the fifth pair. And then you put on the sixth pair. Each one lasting 18 months. So if I have 6 of them and each one lasts 18 months, 18 times 18 times 18 times 18 times 18 times 18. 18 times itself 6 times. It would last, wow, let me see, let me get this number written down. 34,012,224 months. That's a long time. All right, and then the last one here says 80% of running shoes last at most how long if used every day? So, what's typical? Again, they're asking you to find the 80th percentile. So visually, if you have your exponential distribution, and we know that our mean is 18, and we want to know the 80th percentile. So we have 80% in our red shaded region, and we want to know how long our shoes are going to last. Again, it's still just a formula problem, okay? The formula here is K equals the natural log of 1 minus the area divided by the negative of the decay parameter. So for this problem, I would have K equals the natural log of 1 minus the 80% divided by the negative of 1/18. So I have the natural log of 20% or 0.20 divided by negative 1/18. And I'm going to go out to my calculator and do that. You just got to make sure you put enough parentheses around it. Clear this off. We have natural log of 0.20 divided by the negative of 1 divide 18. Close them up. We get 28.9698. So 80% of the time, my running shoes are going to last approximately 27 months. I hope you'll find these extra examples helpful. Again, a lot of this is simply using a formula. You do have to do the calculations in a sense by hand using a calculator, not within Minitab.